Hi, and welcome to 4.7H Atwood machines. In this lesson, students will be able to calculate the acceleration of the components in an Atwood machine and determine the tension in the string holding them together. What the heck does that mean, you might ask? Well, let's talk about Atwood's machine. So it was a person. The Atwood machine, or the Atwood's machine, because it was his machine, was invented in 1784 by the English mathematician George Atwood as a laboratory experiment to verify the mechanical laws of motion with constant acceleration. Atwood's machine is a common classroom demonstration used to illustrate principles of classical mechanics. The ideal Atwood machine consists of two objects of mass m1 and m2 connected by an inextensible massless string over an ideal massless pulley. So basically, the string doesn't stretch, it's massless, and so is the pulley. So you don't have to incorporate the string or the pulley in your dynamics calculations. When the M1 is equal to M2, the machine is in neutral equilibrium regardless of the position of the weights. When M1 is not equal to M2, both masses experience uniform acceleration. So you could study that acceleration and take it from there. This is what an Atwood's machine kind of would look like. So in this example, we have a 4 kilogram mass and a 6 kilogram mass, and it says what is the acceleration of the system and what is the tension in the string. Okay, first of all, what direction do you think these are going to accelerate? This 6 kilogram mass is winning, right? So it's more massive, so it should be rotating this way. We'll talk about later if that's the positive direction. Do we want to make this the positive direction or the negative direction? But for now, maybe you pause the video and think about it on your own. How would you solve this situation? Well, we're going to take a strategy that looks something like this. We're going to draw the weights, but the problem with them both pointing down is it looks like they're pointing in the same direction. But this is making you go counterclockwise, and this mass is making you go clockwise. So they're in opposite directions. The way we have it drawn here, it looks like they're in the same direction. So the strategy is to take your masses and in your mind put them on a horizontal surface. This weight is going this way now, and the 6 kilogram mass, what direction do you think the force should go there? It's opposing that force there. So you could draw it like this and then make your analysis a little simpler. Now we do have the tension in the string, and we'll calculate that after we find the acceleration. To find the acceleration, you ignore the fact that they're even connected at all and just treat it as one block. A total mass of 4 plus 6 being 10 kilograms. So now you use your 10 kilograms and you find the net force. We'll be able to find Fg, right? It's just the weight of this 4 kilogram block. Fg equals mg. So we know this force, we know this force, we know the mass, and we'll be able to find the acceleration at that point. Once we know what the acceleration is, then we can come back and say, okay, they're actually two separate objects and they're connected with a string. Let's look at just one of the objects. We know what this force is. We're looking for the tension, but we know the acceleration is going to be pointing. In which direction do you think it's going to be pointing? Well, block B is winning, so it's going to accelerate opposite where this is. So we know the acceleration, we will, and we know the mass of that one block. We could use Newton's second law to figure out what the net force is. And then once we know the net force and the weight, then we could figure out what the tension is. Okay, so there's a multiple step one. That's just a game plan of where we're going. But before we actually do it, let's take a look at the convention. It says which direction is positive. So it's important to note that the clockwise direction that's going this way, clockwise is negative, and counterclockwise is positive. So it's what they call the right hand rule. That's how you remember it. You have to use your right hand, and then you wrap your fingers around the pulley this way. Imagine holding onto the pulley, and your thumb will point out towards you. All right, so here's your thumb pointing towards you. It's like you're giving yourself a thumbs up. And thumbs up are positive. This is a positive feeling when somebody gives you a thumbs up. If you were to go the other way, wrap your fingers around the pulley this way, you'd have to invert your hand now, and it's like you're giving a thumbs down, and thumbs down is negative. So thumbs down is negative, that's clockwise. Clockwise by convention is negative, and this picture is showing a counterclockwise positive thumbs up. That's your first introduction to the right hand rule. But yeah, that's just the convention, is that counterclockwise is positive. All right, so let's do the problem. All right, let's start by drawing our free body diagram. I'm going to draw them both together in one square. All right, and the mass is the total mass, 10 kilograms. And the FGB is pulling it this way, and FGA is pulling it this way. Now let's write our net force equation. The net force is equal to, well, FGA is pulling you in this direction, and this is the counterclockwise direction, which is positive. So we could write FGA, and then FGB is actually pointing this way, causing you to rotate in this direction, which is the clockwise direction. And we said clockwise is negative. So we'll write minus FGB. Really, I'm just trying to use the convention that everybody else is using. As long as you're consistent, you should get the right number, but it can get confusing. So you just want to use the convention that everybody's using. Even though we said this is now the positive direction, and this is now the negative direction, which is a little confusing because the way we have it drawn here, this is pointing to the left, which is normally negative. But remember, this is just a model. We're saying, okay, imagine it's horizontal. We are talking about a rotating object here, and we should use the positive and negative convention for rotating objects. So, yeah. All right, so what do we know about the net force? The two masses are not equal to each other, so the system is going to accelerate. And if it's accelerating, that means Newton's second law says the net force is equal to m times a. But which mass goes in this m over here? Well, it's the whole system is accelerating. So the whole system is 10 kilograms. You have to use the total mass. Now FGA is equal to mg, M-A-G, minus M-B-G. That's just FG equals mg. Now we could plug in some numbers, so 10 kilograms times the acceleration, and then this is 4 kilograms times, and now we can make this 9.8 without a positive or negative because we already took into account the positive and negative direction. So we're just looking for the magnitude. We made that negative a minus on purpose, so let's keep that. And this is going to be 6 kilograms. Oh, I forgot my units here. Don't want to get points off, all right, times, again, 9.8 meters per second squared is the way to do that since we already took the direction into account. Now it's just a matter of multiplying. So this is 39.2 newtons in the positive direction minus 58.8 newtons in the negative direction. So which value is bigger? Which force is bigger? The 6 kilogram one. So that's what we would expect. And we're actually going to get a negative number here. So if you can continue solving, it looks like this. This turns into negative 19.6. And that negative is really important because it's going to tell us that our acceleration is negative. It's negative 1.96 meters per second squared, and the negative means clockwise. So we know that it's accelerating in the correct direction, what we would expect, because this mass is bigger and we're going in the clockwise direction. Great. So now we know the acceleration of the system, and we can use that acceleration to find the tension in the string. All we have to do is reconsider our model that we have in our free body diagram. Instead of looking at both masses together, let's separate it again and just look at the mass of A. I'll erase all this stuff so we could redraw our free body diagram. Now we have this piece of information, so that's going to help us. So it's up to us how we want to draw our diagram. Now we could actually go back into this orientation instead of imagining it's on its side. So let's draw our free body diagram like this. Our weight is going to point in the direction we would expect it to. FG is pointing straight down, so that's cool. And then the tension in the string. What is the tension in the string? Is it equal and opposite? No, the tension in the string is different from this. And how do I know? Because it's accelerating. Now we know it's accelerating at 1.96 meters per second squared. And what direction is it accelerating? In the negative direction, which is this way, right? Up. So we have to just remember that now negative is upward. All right. So which one do you think is bigger? Do you think the tension is bigger or the weight is bigger? Well, since it's accelerating this way, the tension must be greater than the weight. Okay, so this, we could actually redraw this vector a little bit bigger. That's what we would expect. Okay, now let's write our net force equation again. So this is just the net force for block A is equal to, well, we could write FGA minus the tension, because the tension again is going in the negative direction that we have in our pulley, and FGA is going in the positive direction. FGA is trying to make it go in the counterclockwise direction, which is positive. So remember, FGA is positive, and T, the tension, we think is going to be negative. It's going to be negative. So, all right, so now we have our net force equation. The positive and negative sign is good to go. Now we think of Newton's laws. We know this thing is accelerating, so the net force is equal to ma. And which mass are we going to use? We're only looking at the 4 kilogram mass, so this is the mass of A. And this is equal to the mass of A times the acceleration due to gravity. This is just Fg is equal to mg. And then this is the tension. Okay, so we plug in the mass is 4 kilograms. The acceleration is what we found before, negative 1.96 meters per second squared. The mass is 4 kilograms again, but now we're looking at, okay, this is the force due to the weight, force due to gravity, times 9.8 meters per second squared. And I'm keeping this positive, again, because this is pointing in what we call the positive direction, the counterclockwise direction, minus t. And as you can see, we have one equation and one unknown, so all you have to do is solve. And then when you solve, you actually get a positive number. The tension is equal to 47.04. This is just the magnitude newtons of the tension. We already took the direction into account up here. So if you were expecting to get a negative number, it's because we had the negative up here. If we had made this positive, then it would have popped out a negative number and said, okay, the direction is negative. All right, so it's up to how you make your net force equation. But at this point, we're done. We know what the tension is, and the tension is the same in both blocks. You could verify that by doing the same process for the 6 kilogram block, and you would get the same answer, 47.04 newtons. All right, so we could do the same thing if you want to practice this in a different situation. So now we have a 2 kilogram block and a 3 kilogram block, but one of them is on a level surface. And for now, we'll just say it's a frictionless surface. Once we learn about friction in Unit 5, this is going to become a much more interesting problem because you'll have a frictional force here in addition to the tension over here. All right, but for now, we're keeping it relatively simple and just saying, okay, you have a tension here, which is the same as this tension here, and you have the weight Fg of the 3 kilogram block. The weight of the 2 kilogram block is not pointing in the same direction as the acceleration, so we don't have to include it in our analysis. The weight here is actually just balancing out the normal force here. So that's cool if you want to do something with that, but really that net force equation is just going to be equal to 0 in this direction. However, in this direction, all right, it's not. So we could do that same trick where we kind of level everything out and we make one free body diagram that looks something like this. So the free body diagram of everything together, the mass total is equal to 5 kilograms, 2 plus 3. And we only have this force, Fg. We could call this block A and block B, FGB, like this, just to be specific. Let's see. Okay. So then, it turns into a pretty simple net force equation. What is the acceleration in the system? Well, the acceleration is equal to the net force divided by the mass, and there's only one force. The acceleration is equal to Fgb divided by the total mass. This is the total mass of the system together. So the acceleration is equal to mb times g over ma plus mb. You could write it like that if you want. That's kind of fancy. All right, so you plug in your numbers. And let's see, we're making this pulley rotate. This looks clockwise to me. Clockwise is negative. So yeah, we can still make this like negative 9.8. That's the direction of this force. Okay, and then the acceleration will give you 5.88 meters per second squared in what we called the negative direction. All right, so once we know the negative acceleration, we can reconsider our free body diagram. And should I chance it? I might end up pressing. All right, so now let's see. Now let's just look at block B. So FGB, we have the tension. Okay, so the net force is equal to the FGB, which is actually pointing in the negative direction. So we might as well make the tension is positive minus FGB. So the net force is equal to M times A. And remember, we're just looking at block B right now. So this is in the mass of B. And this is the tension minus MB times G. All right, so the mass of B is 3 kilograms times the acceleration we found to be negative 5.88 meters per second squared. We're looking for the tension. This is 3, and this is 9.8 meters per second squared. So you do the arithmetic, and you solve for the tension. So you end up getting a tension of 11.76 newtons, which makes sense because we found this is FGB over here, and that turned out to be 29.4 newtons. So that makes sense because we would expect this to be greater than that, which would cause it to go in that direction. Okay. One more problem. Let's see. All right, so that one was pretty straightforward because this portion didn't have a force, but now that it's on an inclined plane, all right, it's a little bit trickier. So let's see if you could do it. It says practice, a 10 kilogram block is on an inclined plane at an angle of 20 degrees with a horizontal. A massless rope is attached to the 10 kilogram block, a frictionless pulley, and a 15 kilogram block as shown. What is the acceleration of the system? Does the 10 kilogram block go down the hill or up it? So block A, we'll call this block A and we'll call this block B. and this is 20 degrees. So give this a shot, pause the video and see if you can figure out how to do it, and then I'll put the solution on the next slide. Okay, so as promised, here is all the work worked out. Hopefully you paused the video. If you didn't pause it and try to work it out on your own first before checking this. But basically the strategy is to determine, okay, where's positive and where's negative. B is trying to make this thing go in this direction. So B is making this go, the pulley go clockwise. And oops, we said the clockwise is, I always do that. The clockwise is the negative direction. Did I do that over here? Yes, I did. So I have to change everything. Hold on. Man, just goes to show you that convention can be a little bit tricky if you're out of practice with it. So I haven't thought about clockwise being negative in about a year since the last time we did this. So yeah, the green is negative. This is going in the negative direction. And block A, there's a component of block A that's trying to go opposite that direction. All right, so the weight of block A, there's a part of it that's going parallel to the hill in the opposite direction, which would be the positive direction. So that's why we made this positive, and you could see it's positive all the way through here. And okay, anyway, so you have a component of the weight going in the positive direction, and you have the full weight of this 15-pound block, 15 kilogram block going in the negative direction as shown by our pulley. So you do your net force equation, the net force, and then you sum up the forces, being careful about the positive and negative directions, okay? And then you plug in what you know. It's all trying to figure out what you know. So we know the net force is the total mass of both of these blocks together times the acceleration because of Newton's second law. And then we know the weight is just the straight up weight is mg for the block B. So that's over here. Turns out to be 147 newtons in that direction. And then this block here, remember, we're using only the component of the weight that's acting down the hill, which is Fg sine theta. This is the shortcut. And then we knew that Fg is equal to mg, so you can make it equal to mg sine theta here. And you plugged in your numbers over here. And as you might expect if you looked at this mass is bigger than this mass. So right away you think, okay, the 15 kilogram mass is probably going to win. Not only that, but only a portion of block A's mass is acting down the hill. So not even like the full weight of block A. So that's why block A's weight, the component of the weight, is much smaller than block B's component. And you can see that the acceleration ends up going in the same direction as block B, as long as that's lined up the way it should be. And we turned out to be the negative direction. When you do the math, you get negative 4.54 meters per second squared. So anyway, I guess the point of this one is that even I make mistakes, all right? I never said that I was perfect, and it's okay if you make mistakes too. Believe it or not, it's okay if you make a mistake. It's what you do with your mistake. That's what sets you apart. You want to learn from your mistake. Don't be ashamed of a mistake that you make. Learn from your mistakes. Take it as a positive thing. Just like you wouldn't expect a clockwise to be negative and a counterclockwise to be positive, you might not expect a mistake to be a positive thing, but believe it or not, it is, as long as you learn from it. And that's about it. Thanks for watching and have a great day.